Hello everyone, welcome to another stream. How we doing? Okay, that's good. How's it going? How's it going? So, last stream we're still working on this sort of LOD and clustering system. Just my levels here. So since last stream, I have done a tiny bit of work off stream. Basically, we're working on this sort of refined level of detail shader, which essentially will go over all the highest level of detail clusters and then try and sort of like make low level detail versions of those by going up the tree. Then we kind of got to a point where we kind of like sketched out this function last stream basically, and I've basically finished out the sketch. So I've added this code in, and we'll go over that in just a second. And I think I messed around with this code here as well. So essentially we're just going over the leaf nodes, and we had a problem. I think it's better if I draw this thing out. Hey, there's Rosmuska, how you doing? Happy New Year, guys. Awesome. Hey, there's Sully. Don't worry, the world is still around, Sully. We're fine. We're all good. Yeah, so essentially what we got is things like this. A level of detail system. So there's a 2x2x2 set of spheres. That's a cluster. And essentially at the lowest level of detail, LOD0, there's only one cluster for the whole model. So this is when you're the furthest away from the camera, use LOD0. And then when you are a little bit more closer to the model from LOD0, you're at LOD1, and that has a 2x2x2 of clusters. So essentially each sphere can point to its own cluster, and then each sphere in one of these clusters points to the next one. So the higher level of detail, the more clusters exist basically for that level of detail. So what we've gone and done is built this LOD tree where we've built this LOD cluster tree, and because the way I've designed this is you can essentially like paint down at a specific level of detail, meaning that the leaf spheres, right, the sort of spheres where essentially, what's a good way of saying it? Because technically, be more clusters here. It could be probably up to 8 clusters. Technically, so this is LOD2. You could technically have, you can have like a sphere. You might not have a sphere technically here, but it already will point to another. Also, way of saying it. So when we build this tree initially, you can have this like a slot where the sphere would go. You would not put a sphere there, but you would put, but instead you'll link to a higher level of detail where the spheres go here. And if this higher level of detail cluster, I think I want to say if it's completely filled up with spheres, I might change that. If it's completely filled up with spheres, then a sphere will go here. And this is what this refine LOD shader is all about. So it starts off at the leaf clusters or the leaf spheres, and it basically does that, right? It checks to see if this has a full amount of spheres, and if it does, it will put a sphere in the parent place, right? And it just does that recursively up the tree. That's all that this shader is about. But we have a bit of a problem. Had a bit of a problem last stream, but I think I solved it. Yeah, but I think I solved it off stream. So the problem was, you need to know about the neighboring. Yeah, this was the problem because it does two things actually. So you can have like a 3D volume that's like 1024 by 1024 by 1024, and that's like 1 billion spheres, which is too much. So by having this sort of LOD cluster tree system, is we can be like, well, these spheres are completely surrounded. That's not a really good way of doing it. But yeah, you can imagine like this cluster is completely surrounded by another cluster or something like this. Technically, this has got to be filled like that, but anyway. So we can basically say, hey, this cluster here could actually just be promoted up to a lower level of, or probably not promoted, but demoted down to a lower level of detail, since we don't need the detail inside of the this, because we're simply not going to be able to see it. So we can save memory basically and save space. So we needed a way where we could like quickly look up based on the position in space. Is this cluster surrounded by other clusters which are also filled up with spheres, right? And if that is true, then we can demote this to a low level of detail. So that's what this code is doing here. So I've made, to solve that problem, I've made basically a bit set texture that we set. That we set. And each bit represents a cluster which is filled with spheres. So if we look around here, there's this new shader which I made off stream. So this is another guy, and this one will basically make that I call it an occupation map, right? So it's going to go over all of the. How does it work? Goes over all the clusters. Does it just go down the tree? Oh no, it goes over all the leaf nodes. Perfect. So it goes over all the leaf clusters, and it effectively just writes that to a bit set. Effectively. All right. Hey there, Cranston. It's been a while. Happy New Year. How you been? Been so busy at work, so I haven't caught you in a while. Are the sphere positions quantized? Yes. So they're quantized into not like this right now. So they're quantized into a cluster. So all you need is 2 bits to represent its position, because it's either 0 or 1 across the x, y, or z, because it's a 2 by 2 by 2. We keep track of what LOD we're at, what LOD, got some material index inside of a material palette, and then we've got 17 unused bits. So I reckon we could probably pack this down into a 16-bit integer. That'll be the hope. So we should be able to save a ton of memory there. And then inside a cluster, that's what a cluster looks like. This is also quantized, where it's got 10 bits for each XYZ position inside the volume. It's got a link to the parent node. It's got the LOD it's at, and it has the range of spheres inside a spheres buffer, and then we link to the child nodes as well. But yeah, that's the sort of quantizing we do right now. But we might be able to. Yeah, this one's not quite finished, packing and all that. But yeah, so the cluster node and the sphere are things we're going to have such a high volume of that they definitely need to be packed as much as possible. Basically. Yeah. Progress. This is very complicated. Yeah. I didn't expect me to be on like part 5 or whatever it is, or part 6. Just to sort of work, on this LOD cluster stuff. But yeah, it's been quite complicated to work out. But yeah, it's good though. So basically we've got this texture now called this sort of like occupation map. And so it's a 4x4 bit set. Yeah. So we kind of do this trick where we repeat. Yeah, to make the sampling really easy. Like, okay, so the problem is, you have like a bit set of, ideally when you have a cluster, you'll have like, you need to know if you're completely surrounded by full clusters. Let's see if I can just draw these clusters out quick. So instead of you're completely surrounded, it's a bit of a bugger, right? So it is a bit set, right? So because it's a bit set, like you need to check all of these bits around you and not this one. So, if you was to have like the boundary could be, you could be like, yeah, so, you have to use 32-bit integers on GPU, but technically you could pretend it's a 64-bit, in a way, integer, and that way you'll get a 4x4x4 bit set or something like that. Oh yeah, and you have to check them in 3D space as well. So there's 8 checks you have to do here. And then you have to do them like 8 more going forward and 8 more going backwards. So that's like 24 checks. So that could potentially be, 4 samples or more of, which is quite a lot. Or maybe even 8 samples, because there could be 32 inches instead of a 64-bit. So to solve this problem, what I did off stream is I made it's a 4x4 bit set split into two U32. So you just imagine it as a 64-bit integer, for instance. 64-bit bit set. So it's split along the z-axis, but we address it using 2x2x2. So we basically use the final 2 rows, columns, and slices as a repeat of the first 2 rows and columns from the next bit set. So essentially what you get is these two, so it's a 4x4x4. Let's draw that out in 2D space. Just be a 4x4. There we go. So it's effectively like, if we want to check if a cluster has any neighboring spheres, we just work out its sort of like, so all of this data here is a repeat from the next sort of like bit set, basically. Is that right? Hard to imagine. Still think about it. Hey there, Cat Payne. You've done a half gone by the end of the year. You failed this year. No. Yeah, well, I still won't be grey. You got a while for that. But yeah, I'll probably get a haircut at some point soon. Till it gets a bit long. But yeah, the beard will stay until I get that haircut. Happy New Year. So essentially, we're able to cut it down to a single sample because the final 2 rows, columns, and slices are repeats. So that means we basically land our sample point within this 2 by 2 by 2. We never land our the center point of the sample. We always land it within this 2 by 2 by 2. So that means if we want to look at this cluster, we can literally just check around in this bit set here like this. Or if we don't want to look for this cluster, we can see if it's surrounded by checking the bit set all around here, right? And if we want to go and grab this one, well, we just go into the next bit set of 4 by 4 by 4, and this will be repeated information, right? So all of this and this and this is repeated in the next bit sets. And this one is repeated in the previous bit set, something like that. Is that right? Something like that, anyway. So it means we can basically just do some little trick like this. That's pretty crazy. But so we treat it as a 2 by 2 by 2. So we index it as a 2 by 2 by 2, and then we'll land inside one of these positions. And then we're inside there, we can just check the neighboring cells with just simple a bit mask, basically. And then just see if we've passed by checking the low and high end of the 64-bit integer. Because we have to check 2 32-bit integers because it's the GPU, we don't have 64-bit ints. So that's the sort of trick we're doing. Although I thought off stream that we need that there's something to do with the z-axis because we split. So it's a bit of a weird thing that we do. So because we do this is it. So effectively we've got a 4 by 4 bit set using U32 split along the z-axis. And we address using 2 by 2 by 2s and repeat the final 2 rows and columns and slices. But because it's split along the z-axis, right, it's technically a 4 by 4 by 4 by 2, right? Which means when you repeat it, those last two slices, when you repeat that whole bit set, let's think about this. Hey there, Arhana, or Hunter, Well, how's it going? Welcome. So there's a 2 by 2 by 2 by 2. So along the z-axis, where's it repeated? Yeah, it's repeated at this. Oh, isn't it? Well, hello, Ransel, how's it going? Thank you so much, sir. Appreciate it, 8 months. Appreciate it. How you been? How's it going? Give you one of those salutes. Thank you, sir. Happy New Year, Happy New Year. Alright, so where's this code taking us? So if you're non-zero, go back. Yeah. So ones at the start get repeated at the back. Okay, yeah, so I think because we're splitting across two U32s, the Z is basically redundant. Like, we're just wasting memory at this point. So it's a 4x4 bit set split along the Z-axis. So we shouldn't have to reach back, because if they just check the next bit set, is that right? Yeah, just the, so... Yeah, so because it's split along two U32s, like bit set... Wait, is that right? Yeah, because it's split along the Z-axis, so Z 0 and 1 will be different, but then like 2 would basically be the same as 1, right? And 3 would be the same as 4. Yeah, that's what I was thinking. So effectively, we don't need to repeat the Z. We just have to sample it differently or something like this. Just gotta make sure these coordinates all make sense now. So what do you... so the way we sort of address this bit set... so that'll make one less right back to... Make one less right then. Yeah. So highest LOD cluster coordinate. So it's the cluster coordinate just in cluster space at that level of detail. Oh no, the highest level of detail. Yeah. So the cluster coordinate, the highest level of detail, this is how we're writing into the bit set. So the bit set is there's one bit for every cluster at the highest level of detail. That's right. Then we add one for the empty border around the outside, so that avoids if statements when we sample. And then we divide by 2 along the XYZ, and then get a coordinate. We times by 2 because there's two U32s, but because we've removed that, we're squishing them now. So how would that work? Yeah, we shouldn't have to do times by 2 now. Bit coordinate. You end up doing a 7th constant December on the 30th. Awesome. How'd it go? Was it busy? So this gets the bit the bit coordinate in 3D within the bit set. Then we flatten it out into a index. So that's your bit. Yeah, that's the bit you're gonna set, right? Then you basically atomically all that into that U32. Sends that 4x4x4. And you'll simply be addressing the first 2x2, right? And then we essentially reach, if we're not at the first bit set along the X or the Y, we reach back into the previous bit set, and then we put it at the final, in the final 2x2x2 for that bit set. Now, so I did something with the Z now. We've removed the extra Z bit set. So they no longer repeat along the Z axis, simply the way we sample. So if you coordinate 0 or 1, yeah, I think that works out fine, because you'll be at coordinate 0. So coordinate 0 will get added by 1 right along the Z. So you never land on coordinate 0 because there's an empty border on the outside. Then, you know, you'll divide by 2, mod 2, right? Yeah, it should be, yeah, that'll be right. So when you're at Z coordinate 1, you're gonna land, yeah, you'll land here, right? So 0 will get added and you'll land in this place 1, and then 1 will get added and in this place here, right? And you never land and write into these places around the edge. Those are only for repeats. Something like that. Is that right? Oh, no. Sorry, it's modded afterwards, isn't it? 0, 1. Oh, yeah. Sorry. Yeah, no, it's not right. Yeah, so 0 land there and write to it. 1 will land here, but then get modded back to here in the next bit set over. Right, so we added 1. Okay. So for the Z axis, that'll still be fine, right? Yes, but we don't reach back and write anything because it's already been repeated. Excellent. So this means when we do the addressing, when we read from this, I've got to change this comment. So it's a 4x4x4 bit set, you split along the Z axis, right? It's not, okay, it's a 4x4x2 bit set, right? Yeah, bit set. But it is addressed using a 2x2x2, and we use the final 2 rows and columns as a repeat of the first 2 rows and columns from the next bit set. This allows us to get away with loading a single loading 2 U32 bit sets when checking our neighbor clusters, right? That's pretty cool. So we only do this providing that the spheres count is a full cluster. We only bother writing anything out. Okay, that's really cool. So now when we read this, so this is the pretty cool trick that we get to do. So it means we can check it with 2 loads and basically just checking some bit sets. So that it should be pretty quick, hopefully. And the alternative that was thinking about would have had to traverse the tree and find nodes, or the other solution was put it in a texture and do a whole bunch of samples. So this is putting it into a texture as a prepass and then doing 2 samples and intelligently working out the neighbors if they're set or not. So that should be pretty ideal. It went good. Got home 31st though because no train. Oh, crap! Did you have a friend's place to stay around, or did you anything else? Did you have a good place to stay? Oh, nice peppermint tea, yeah. Oh yeah. So now we're just gonna get this addressing right. So man, this code is so complicated. But it's good. It's gonna be good. So we get our cluster coordinate, right? Is it in the highest LOD space? So we're going over the leaf clusters, right? Oh no. Right, that's another thing I forgot to say. We then, okay, I'm glad I remembered this. We got this, so we build this occupation map, right? Where each bit is a cluster. What we're writing to here is the highest or the lowest MIP, right? And then we build a full MIP chain, right, going up to the lowest level of detail, or the lowest level of detail. So then, when we do our sampling here, we need to load from the MIP chain. So I need what I actually need. Aha, LOD count. That's a bunch of these guys. What did I do with my? Did I do a way where I could just add numbers? Can I check my GPU thing? Texture in it. Yeah, I think it makes them in a linear. It linearly allocates them so that they can just be addressed. We can just add to the resource ID and get the other one. I think that's how it goes on. Oh yeah, you need to make the views. That's it. Oh, I'm not sure if I did this yet. Right. Yeah. So in future, you want to make. Okay, I got an idea. Right. So in future, we'll do that. Okay. So what this needs to be here is based on LOD. There'll be node. Where is it? Is it cluster node? Node.lod. Awesome. Review that sleepovers here. Oh, okay. It sounds pretty rough though, but still, at least you got home in the end. It's always the worst when you miss the train. Yeah, you have to like ring someone to pick you up. Or crash somewhere. Or get a taxi back. Right, so the way we did the addressing now is different in here, right? So this is at this LOD. Yeah, I need to write a downsample shader, a very specialized one, because the way we do this repeating actually. So we add one for the borders. So we can check with our if statements. Excellent. So 3, we divide and mod with 3 here, as we want a 1 cluster border in the 4x4x4 bit set. Yeah. So yeah, we have a 1x1 border all the time. Interesting. Yeah, so for 0, 1, for 0 and 1, so 0 will be added to 1 and it'll go to here, right? And then so 1 will be added and it'll go here. So you would, you know, this would be like your mid sample position within the bit set. But when you do a 3, your 3, sorry, when you do a 2, you add 1, so you get 3. So that'll go into the next bit set. No. Yes, yeah, that's wrong. Because you'll end up at the start. And we never want to end up at the start. So it's as if the add needs to happen after the mod. Or whatever it is. So you do the modding by... So you do it by 2 still, and then you add 1. Something like this. Yeah, that feels right. So you still mod it by 2 and divide by 2. That way it addresses correctly. But you add the 1 after. But what are we adding the... we just add it to the bit chord, I think. So I'm curious, are we doing that in the right place before? Like, we're inconsistent here, is that fine? So it's a 2x2x2. Yeah, the add has to happen before. Because you want to be writing to these 2 places here, and you only be reaching back to write to the rest of them in the other bit set. Yeah, those are repeats. Okay, that makes sense. Whoops. So here then, you do the add afterwards. Okay, so it is a 2 still. So we add once we check with no if statements. Add 1. Add 1 so that our sample point, our center sample point is sort of like around. I need to put this in a better place. the empty border, so we check our if statements, and so that's our center sample point is surrounded, I can't spell this word, surrounded by surrounded by bits within a bit set. Is always surrounded by bits within a bit set. So that means if you get 0, you'll go here. If you get 1, you'll go here because we had 1, right? If you get 2, you'll go into the next bit set and you'll go where 1 is in here, right? Excellent. So even on the z-axis, that's what you want, right? And even on the z-axis, so the z's a bit trickier. Yes, on the z-axis you do want to be like that, isn't it? Yeah, you want to be on the... Yeah, the z-axis you want that as well. Excellent. So this is the crazy little trick, basically. Given your current coordinate, so it's a 3D coordinate, right, into the bit set texture. So each bit set has a 4x4 by 2 of clusters, and when the bit is 1, it means that the cluster has a full set of spheres of 2 by 2 by 2. So this means we can use this bit set to check if all of our neighbors have a full cluster, and if they do, we can then demote our cluster. We can get rid of it and then say, hey, this thing is now a lower level of detail, and we just do that going up the whole tree. So we get, so you know, 2 samples instead of 8 or more, thanks to the repeated information or repeated cluster bits. So then we add 1 to the z-axis to get the next. Like, so if you've got z-axis 0, you'll then be added to 1. You know, with inside the bit chord, right? And then if you're on 1, you'd have gone to wait, done. This is what we want. You've been you go to 2. Yeah, that's what you want. Excellent. That's good. That's good. That's good. So effectively, here's what we can say, right? As another way to help people understand this code and me in the future. You want to say basically bit coord will, you know, will either be 1 or 2, right? Basically. Bit coord sort of like elements, or sort of yeah, will either be 0 or 1, right? Sorry, be 1 or 2, that's what I mean. So basically we set up a bit set now to represent this, a way to check all the surrounding bits. There should be. Alright, we're good. I nudged the cable somehow. I don't know how I did it. All right, Elspil, how's it going? How's it going? How you been? Merry Christmas, Happy New Year. Welcome to 2024, where Mickey Mouse is now in the public domain. Dun dun dun. It's happened, guys. Mickey Mouse. Public domain is here. I've been saying it for years. Yesterday was the day. Mickey Mouse content will be everywhere. I'm writing a little UI library in C, and yesterday I started working on a text widget, and now I want to DIE. Wow. Yeah, writing UI, like, it's fun, and you can cut a lot of corners when you don't need stuff. But yeah, writing a text field isn't that bad. Writing a multi-line text field there's a level of problems there, and then supporting UTF-8 and all of that. That's probably 4 times as hard as the multi-line text box, and then you've got there's kind of lots of stuff you can keep adding to UI stuff. Yeah, nice. Yeah, it's cool though. Custom UI all the way. Good stuff. Yeah. So we'll load those 2 buggers in. We set up this lovely sort of so there's 3 possible configurations here. There's EE0, there's EAE0, and obviously 000, and this is the bit pattern in as 4x4 by as 4x4 slices, and obviously there's 4 of these guys across these 2 32-bit sets, right? These are 16 bits, and there's 4 of them, right? So effectively, we just say, hey, if z is greater than 1, then we need to have 0, 0, 0, 0, then e 0. So that what that's saying is that our center sample point is inside the bit set index 1, right? It's inside the last one. So basically, we need a wall of zeros, and then we need a wall of ones, effectively. And then if it's not there, it means that it's actually within the middle sample point is inside the first bit set 0. We need a wall of ones and then a wall of these guys, right, where the middle one is missing because that's where the sample point is. Yeah. And then we work out the sort of next bit set by doing the same sort of thing, right? If it's greater than 1, then it's this thing with a hole in. Then if not, it's the back wall. And then if the sample point is in the first bit set, then we just have the wall, right, which covers the other end. So this means that you've got 2 32-bit bit sets. You can imagine it's one 64-bit one, but the idea is there's a bunch of bits that purely represent a sample point, which is going to be 0, and there's a bunch of ones going all the way around the outside in 3D, right? And remember, each of these guys is a cluster which represents a 2x2x2 of spheres, with all of the spheres on, right? And providing that this is true, and we have a full set of spheres ourselves, then this means, and then we do some shifting here to sort of the x and y coordinate, right? If because this middle position technically might be a cross by 1, right? And if that is the case, we shift it over, right? And then if the y itself is wait, is this right? Because this is going to be between 1 or 2. Yeah, that's right. We take 1. And then we'll obviously shift it down by a whole row. And after that, we can say, hey, with this simple check here, is our cluster child cluster? What does that even mean? I'm not sure if I need the 0 in the middle, to be honest, because we shouldn't because this guarantees, right, that this is not 0. So I don't necessarily need that. So I could actually simplify it even more. That's a good point. Hey there, Not So Red. Happy New Year. How's it going? Not doing bad, not doing bad. I started back at work today. Yeah, things were good. Did some got got cracking away at trying to finish off my current big task that I kind of left split over Christmas. But yeah, been good. How about you? How's the new year and everything? That must mean that we will see a sphere-based Mickey Mouse in this engine. Of course we will. Of course we will. Gotta. Yeah, maybe we should just go for Mickey Mouse and just that should be one of the constraints on the game design, is it has to be a Mickey Mouse game. That'd be pretty crazy. I think I'm quite late on the game. It's probably gonna get milked pretty bad. But you never know. We can see what the landscape's like when we do the game design. But I'm sure people have been sitting there waiting for this Mickey Mouse thing to be available. But we can always have him as an Easter egg. We just shouldn't design it around. Yeah, so it needs 3 spheres. Exactly. To be fair though, that classical Mickey Mouse logo is not quite the original. That's still copyright, fortunately. Yeah, that's right. That's right. That one's still copyright, right? You need to do the original sort of steamboat, steamboat Mickey Mouse. You know that one. Hey there, Mr. Dick Still, how's it going? Can my engine do 3 spheres? Mate, I could do 27. Yeah, there's videos on the VOD channel. But we're currently like midway through making it go from 27 spheres to like thousands of spheres. So it's involved. Yeah, that's right. Excellente. Yes, we shouldn't need that. So we can actually remove this, and this can stop frying people's brains. Or it's going to reduce people's brains from overheating. So technically we can just make it like that. So, and shift them to the right place. I was so happy when I came up with this. I was like, man, this is awesome. So hopefully it should be much quicker. And you say, so what I'm saying child cluster is surrounded, what is that talking about? Right, so you're getting a node. Right, you're looking at the child clusters. Wait a minute. But you're looking at the leaves. What are you doing? Right, create a, oh, I see. So the first one, this is, right. Can't be true. Oh yeah, so this would be skipped for the first iteration. Because if you're on a leaf node, you're not going to have any children. No. Yes. And then if it is a leaf, oh my days. To work this one out again. If this is a leaf node, move it from the non-leaf array to the leaf array. Right, I forgot where the leaf array is. Isn't it before the midpoint or after the midpoint? Something like that. There's a cursor, and then before the cursor is a leaf or something, and then after the cursor is a non-leaf or whatever it is. So right. Seems like this thing is just gonna. Right. If this is a leaf node, move it from the non-leaf into the leaf. So given our node, get the child index. Right, how are we doing this? So we're getting 4 on the along the air. So doing 4 nodes per wave. We're doing 8 children, right? So it's 32 in a wave, obviously, right? 4 times 8. Get a volume. So you get a leaf. Yes, you're going over all the leaves. Pick it up. Because it's a leaf, it's not going to have any children. Okay. Child index equals mod. Is that true? Right, so we're updating the child index here. So given the current node, right, so that works out the child index within the parent. Okay. Within the parent. Then we get the parent node index. We check if it's visible. Sorry, no, we've visited this node already when we're doing this sort of refine level of detail thing. Then we go yeah, then we get the bits. Right. Okay. So we kind of want to say like these are all the visit bit mask or bit set since it's in the higher bits. Visit bit set is stored in the higher in the sort of 8 to 16, 8 to 15 bit range. Something like that, right? So if we've visited all of those guys, we are the last child to visit this node. So you have a bunch of threads. So if your cluster has a bunch of child nodes, and when they all visit, when they've all visited, so you want to do this providing that you go up to the parent. We haven't said, hey, if I've not got a parent. Right, how do we... I'm not sure if it stops that. So that's just going to keep on going. Yeah, so you're going to say like, hey, if node.parent node index is not equal to U32 max. So this one's saying we are the last child to visit this parent node. So, and then we'll carry on. So then we go back up to here and go again, and then check all the children, and if, they have a full set of spheres. Sorry, if the cluster, if they have a full set of spheres for this child. Yeah, I think I'm doing something wrong here. This is meant to do two things. Oh. Right, we've got to write code here to create the lower LOD sphere. Yeah, so if there's a full set of spheres here, you need to create the lower LOD sphere. So we need to actually write that code here. And then this is saying if the child node is a leaf node. Yep. And it's completely surrounded by other clusters with full spheres. Then we delete this child, but we still keep the LOD sphere there. Got it. Let's make this lower level LOD thing. Did we allocate any spheres in the previous on the previous shaders? We must have done, right? Right here. How are we gonna do it? Doing good too. We did team building trip last week. Wow. Oh yeah, nice, awesome. How far did you go? And how long was it? So where do we make a sphere? We're copying the spheres here, isn't it? Yes, this is the allocation code, right? First thread will allocates a contiguous set of spheres, right? So we should just copy this code. So since we own, like, this is the thread, like one thread per node. So this is safe. So what we want to say is if right? Well, would this always be the case? Yes, only the leaf. Only the leaf. Yeah, so I think we need to put some form of like, is there some debug stuff that I've got going in here? Could have swore I did some of that. We need to put some form of like GPU warning or assertion type of deal. Because this will get quite... Right, let's write this out. So we're basically going to say like if, you know, debug or whatever, you sort this out. But here we want to say, right, node dot I could do a cert. We need to build a cert into this. But assertions we should probably only do in debug time anyway. So we should really build something like this. So what we want is right, let's comment this out for now. So the assertion needs to be node dot spheres start index. Shoot, that doesn't look good. Oh, come on. That will never be the case. Because it's bit set now. So we need to get 29 bits turned on. Define volume cluster node spheres spheres invalid. That'll just be one shift left, 28, sorry, 30 take one, right? Oh wait, it's 20. Yeah, so this thing only gets set providing that yeah, so that's the assertion, right? So the comment would be like, you know, the leaf. So we expected only the leaf spheres. Wait a minute. No, you've got 4 threads per... You got 4 threads per node, isn't it? Sorry, 8 threads per node. That's very true, isn't it? We need to have a way. Problem is you've got 4 nodes in a wave, and there's 8 children per node as well. Some of the nodes might not be. You might have overshot the number of nodes. So each one of those that have missed is 8 less threads going at a time. So because you've got 4, so all of them are guaranteed to be running. So you basically just need to say, hey, if child index equal 0, this is where we'll do the allocation. So it's got to stop. You might as well stop traversing up the tree when you can't really create a lower level of. Oh no, you have to go all the way up. You have to go all the way up. Yeah, I know, right? It's pretty complicated code. Just, I'm not sure how I can make this any easier. It definitely needs a lot of diagrams, basically, to understand what's going on. No, I think we want it to be equal to invalid, because we're going to allocate it here. We expect only the leaf spheres. The leaf nodes, leaf cluster nodes, to have spheres at this point. So here we're going to actually allocate a contiguous array of spheres of 8 spheres for this cluster. Like, do we need this? We might not need it just yet. So you do 8 of them that go. We store an LDS in the previous. Yeah, so we might want to store them in LDS. Did that up here. Right, I think I just need another one of these. What do we call this? Refine? Refine LOD, LDS. So what do we need? One for each node. It's probably the same thing, isn't it? So basically this thing needs to get initialized. So here, if child index equals 0, we want to initialize the LDS. We need do you call it cluster index? Something like that. So you'll be like cluster index dot spheres count equals 0. So you zero initialize all that. Do we need to zero initialize all the spheres as well? What did I do in that? Because you get one thread to do it, so it can all just be done in one line of code. Did we do that in the previous one? Yeah, we did. We just set the radius. Gotcha. Child index is what we call it here. Right, so we set up the LDS there. And the reason why we use LDS is because we might not actually need to allocate the node. We only need to allocate the node providing that the sphere, we actually have make spheres. So here we're going to make the sphere. So again, we go up to the code above, or we did that, it was here. So create the lower LOD sphere. So we need to use I'm not sure how I could have made LDS better in the compiler, you know. Like, it could have maybe have been something you pass around as a pointer. But yeah. I don't know. Shaders are just weird. Shaders just so silly. And plus, I don't really have proper pointers in this thing anyway, so it's all got to be like that. Okay, so the center position. I think we just use child index. So mod 2 wait, how do we so go child indexes from 0 to 8 or 0 to 7. So mod 2 will get you across the x. It's across the y divided by 2, and across the z if greater than 4. Greater than 3. So it's new if the radius is 0, because we initialize it to 0. So what we've got to get is, so the main thing we need is this. You need to look at the child node's spheres. You need to get those, and you need to get we need to somehow give it a material index. So every sphere has a material index. I was hoping to pick so given the child node, so you have one thread on the child node right now, but that child node has another set of 8 spheres in there, which kind of sucks. Because we need to kind of know yeah, because I don't want to write like 8 lines of code to work out well, more than that, to work out which, it's basically get all the indices, and you want to pick the one which is most common. That's the kind of idea. We could just pick the first one for now. See how that goes. So we'll just grab it from mm, 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 mm. So where's the child node? So that would be... Any more of these boys dot about? Nope. Yeah, so for now we'll just do child node dot spheres start index plus, yeah, it's gonna be proper dodge. Right, so we've got to work out some kind of like material palette material index. It's gonna be a bit silly. So here would just be like, to do, this just picks. So it's only possible because you've got full set of spheres. Yeah, okay, so this would be safe. This just picks the first sphere, sphere's material, finding a way to sort of select the most common properly, or do something else. This is something to work out later because, yeah, it doesn't matter right now fully. So we're going to flag this bit so it's the auto-generated LOD. Not sure how useful this is actually going to be, but it could be, I don't know, in the future. What LOD is this? We don't have a construct LOD anymore, but this LOD would be node.lod. I think that got filled in. LOD equal do we have like a .lod somewhere? Right. Allocate child node. So that got added on. Yes, they all get set up, which is good. Okay. So is that all legit? Then we add 1 to here if to the sphere count if this is created. So right, that's good. So now so that sets up LDS. Here we put it into LDS temporarily because we might not actually need to allocate any. And we will know after here. So here we know, if we need to look at that LDS thing again. So it should just be as simple as if this and that. We have found spheres for the thing is those. All right, I just thought about something. So you could have painted down on a certain level of detail a sphere in a cluster, but then there could be at a higher level of detail other spheres, which then would have been painted down fully, that would have then gone up the tree to the one, the parent one, but for a sibling of it. And then you would sort of fill in that one. So this might already exist, thinking about it. Right, so when you go over this for the first time. Wait a minute. So when you go over this, right. So if that ends up being the case, you need to say, so there's this if statement here where we say it's all been visited. This visit thing needs to actually happen. Earlier. That'll go up to the parent. So I think regardless, you go up to the parent. So we could probably rephrase that as simply, hey, if there's no parent anymore, then break. Maybe yeah, something like that. We can play around with making that better in the future. If this is a leaf node, move it into the yeah, so that comment there was for me to there's no moving happening here. Anyway. That code needs to be finished up at some point. Right. So here we get the node. We go, hey, by the way, let's delete all that. So we don't need to do this child index thing anymore. That needs to go down here. Same with that there. That will traverse to go up to the parent node. All good. So this one's saying, hey, I'm visiting this node, and what we're going to say is I'm visiting this node, and only if it's completely full. If it's not full, we then want to break. We are sort of not the last child to visit this node, something like that. No, because you're going to get one thread per. Damn it. This is going to set all the children in one go because you're getting one thread per child at this point. Ah, crap. No. I don't think that's a problem. I just was going over. I just thought about that too much. That's wrong. That is wrong. Okay, that is fine. Ignore that. That was not. So if you've painted at a low level of detail, but there ends up being some sibling spheres which have not been painted on, but they have child nodes, that node is not a leaf node, so it would never start there. That's what it is. Yes, that'll work. That makes sense. That makes sense. Okay. So, right. So where are we at now? So we've created this low LOD sphere. This block of code is saying like, try to remove the child if it is completely surrounded by other clusters with a full set of spheres. So there's 2 bits of code we've got right now, and then we should be done with the shader. That is delete the node, and this one here, this piece of code here. I nearly missed that one. So if this node is a leaf node, we need to move it around inside the node array. So each volume has a cursor position of cluster tree midpoint cursor. So on the left-hand side is the leaf node, so the negative numbers. On the right-hand side, it is not a leaf node. So by doing it this way, we have sorted our nodes into leaf node, or we've sorted our leaf nodes into a contiguous place of memory, meaning when we want to start to ray trace from these guys, well, we want to start from the highest level of detail on the leaf spheres, or on the leaf nodes, and go up from there basically. So it makes it really easy to sort of dispatch shaders. So we need to write that code. So there's a bit of a problem though with these 2 things. We need to make sure that we're not, it's highly threaded environment. I don't think deleting of a child can be done while we do this, and maybe moving as well. We'll see. We've got to think about it. Just take a nice sip of H2O here. There we go. So essentially we've got to move it to get that volume. Volume, if I can spell. Not that one, this one. So here's our midpoint cursor. The leaf nodes come before the non-leaf nodes. So it is already inside. So what we can guarantee is the current node that we're looking at, no other compute unit is at this node. There's 8 threads on the node, but they're all within the same wave, right? They're all inside the same compute unit, and each one of those threads is targeting some child within that node. But we've already visited all of those children, and all the threads are sort of executing together in that. So it's not a hard problem to solve, right? In that case. So But you got to move it from. So there's a few things, right? So when you delete a child, that could be a leaf node, or it could not be a leaf node, right? But then when you delete it, what you kind of want to do is grab. You want to do one of those sort of like like how you remove it from the array. It would be nice if you have your array. Maybe your midpoint cursor's here. So all of these guys are not leaf nodes and these guys are leaf nodes, right? The idea would be is like, hey, this one is no longer a child. Wait. Yes, you'll only be removing leaf nodes here. So you'd be like, hey, this one is no longer a node. No longer a child node anymore. So what I can do is I can copy this node over to here and essentially just say, hey, I've got one less leaf node, so essentially it's going to move that cursor to there instead, and we just forget about this guy, right? But the problem is this could potentially be accessed by another compute unit. We can only guarantee that this one that we're deleting is being removed, right? And I think that's the same for this moving here, right? So I think what we need to do, we might have to break into another pass, but there might be an intelligent way to do this. So these ones are only leaf nodes, right? These are leaf nodes. Whereas these guys here, so you've got a node and you're going up the tree, and what you're saying is, so maybe you've deleted all the children, because you've figured out that all of those children cluster nodes are all surrounded by other forecasters, which could be quite, it can happen quite a lot. So this would then mean surrounded by, yes, this would then mean you would move this from a non-leaf node into a leaf node. Would you ever move something from a leaf node into a non-leaf node? You'd never do that, right? That would never happen, because to do that you'd have to create more children, and we don't do that in this. We start the leaves and we go up. So we basically want to say is like, if we fully deleted our child nodes, and that's interesting. Do we save this as a leaf? We don't save they're all leaves. Will anyone do this if this is a leaf? If children bit set, you kind of want to do something like, where's the bugger? Oh, there's references as well, isn't there? You got to patch those references. See, patching the parent, no, patching the references isn't that hard. You just go up to the parent and find your child index, and voila. Pretty simple. But so you want to say, and this is less than 0. Child is leaf node. So only if the child is a leaf. Oh no, we already do it here. It's right there, damn it. Okay. I've already done that check, that's good. If the child is a leaf node, if it is a leaf node and is completely surrounded by other clusters. Excellent. Rightio. So only if you've fully deleted the children. Right, so I guess that could go in here. Let's just think about it. So you're running this in lockstep, right? Each of the child threads will be running, and this one will be yeah, so beyond this point, each of the child threads will not be, active if it doesn't exist, if they're all not set, right? So if we've become a lead, that's, yeah, but the ones that are active will be running that matter, that's fine. So they'd all go in here, right? If they've got a full set of spheres and we try to remove them. Delete the child. So I think we could put the if statement in here. So this is the only place where we would need. I think that's right. Let's double check that. So you've got if the child is a leaf, so our clusters. So we delete. Then this one is, you kind of want to say, right, if sort of like child index equals. You don't kind of know that. You kind of just need to say like, that's part of the issue, isn't it? I guess you need to, at this point when they're all active again, you need to say, hey, if the child index is 0, we need to, a nice bit of code, which would like, just do this. So we need to say like if, so in here we need to go like, oh, we've deleted it, and the node, we need to like modify that node bit set. Maybe and like remove the children from it or something like that, okay. So we'd have to do that, so we can put that in the if statement here. And if they're all gone, you can then do the removing. So now we just got to figure out if we can do the removal now, like do the moving around now, or we have to sort of like mark these nodes and say what they are, and then like rewrite the array in some future pass. Yeah, it's any more difficult thing. So so your thread owns the node that it is. So it's deleting a child. Those would be in the middle of the array. More than certainly, and be in the middle of the array. So you would have to create holes. you end up creating holes. If we the other way of the other way to solve it, if you could do it in a second pass, is you could pump out into an array a bunch of indices, right? And maybe all of the nodes would have been created, so it doesn't matter if you delay this action. So you're going up from the root leaves, going all the way up to the parents. You jot down all of the ones you want to get rid of. Right. Or maybe you just jot down the ones you want to keep. And then we can rewrite that into a proper place. And that's probably a way of looking at it. So so after you've done the refine, okay. So we just now need to keep track of like some form of bit set. So you have like the children bit set. So if you put a bunch of indices out into an array anyway, you could just do the copying then into the new place. So I think you could just do, but you won't know the number of nodes that you have at the end. So we need to probably count up. Oh, it's a bit difficult. So we could make a whole array of indices that would take memory. Or we could simply just mutate the node. So you can mutate the node and say what child and so maybe you have like children bit set equal this one here, right? So I think what you could do is you can mutate this. So here you're just going to delete it. The not of one shift left child index. You probably want to get rid of the one from the visit bit as well. You care about that? You care about the visit bits at this point? Right, so because we're the first thread, we want to say if so that thing is not set to anything versus hey, it used to be set to something. Right. Now this means we are now a leaf node. Right. So we could just update. So your two solutions right at this point, you could then update the nodes, put the new bit set data in, then you run another shader after this, and you'll probably traverse up from the original set of you'll traverse up from the original leaf nodes which you we've started from in this shader, and you see if we could probably mutate the child node spheres count, set it to 0. If it's equal to 0, we just don't copy it into the new place. But we maybe keep track of a oh damn, you can always misspell that. So you set that to 0. So the thread looks, so he goes, oh, it's 0. We're not going to copy this guy. If it's 0 and if the children bit set is 0 as well, right? Yes. So all we have to do is keep note of an overall count of how many how many nodes we're going to have. We can know how many leaf nodes and non-leaf nodes we're going to need. And that is what we need for the next thing. So ideally, so we've got this volume. Yeah, I was trying to think, is this the best approach then? So the approach would be, we just sort of like retraverse the tree again. But now we know sort of like how many nodes we're going to have, so we can pre-allocate the new place in memory, and this will be the final destination of where this guy goes, right? Because right now it's in some temporary, we have some like, here's the maximum thing that could ever be made, and this is like our building space, and this is where the nodes go in initially, but they need to be copied out anyway. So to copy them out, we need to kind of know the count ahead of time. Oh, we need to know the overall number you're going to have. And to know that, you have to sort of run over this code, right? So the only other approach is that you write out a whole array filled with indices. And those indices, you just launch over a shader, which just picks up the index from the buffer, takes that, and then it allocates it into the new range of nodes, the perfect range of nodes, and it patches the child indices. So it's that versus traversing the tree again. So it's just a case of like, what is better, right? Either producing another whole array or just traversing up a tree again. Yeah, so I'm not sure what is actually better in that case. You know, I don't have to make another array if I just traverse up. I just have to make sure that the visit bits are set back. So we have to set the visit bits. Oh wait, you can't do that. Because it's not a reference or anything, is it? Because GPUs and stuff. You know what, like as soon as I've like completed this project, I need to like go back into my compiler and add some form of pointer support, because this is just dumb. Just so dumb. Shaders suck. But yeah, I need to like basically do that. Yeah, so you set that back. So when you traverse, like you've got rid of the visit bits at this point. remove the visit bits. So the visit bits will be removed. The visit bits would have been removed. Awesome. So we've just got a new set of children now. So this is saying like delete child. Yeah, so we say delete that child. These are blah blah blah. Only remember these are only leaf nodes. Remember are only leaf nodes. And we also want to say like the child is properly deleted. Properly deleted later. Deleted in the next shader. So here we remove that, and we set this here. It's a leaf node. There's no children, then you would have got rid of the spheres. Excellent. Sweet. Do modern GPUs support arbitrary pointers? I'm out of the loop. So SPIR-V has pointers when you compile stuff out, but they're logical pointers. So what a logical pointer means is the compiler has to know. What's the way of saying it? You can't conditionally reach that address. I think they sort of added it in later, but that's the simplest way to explain it. You can't conditionally reach the address. That means that you can use you can have like a variable index, or whatever, but it just means that the pointer itself isn't generated conditionally. That's the way of saying it. But arbitrary pointers, like proper pointers, like stuff we should have had for a long time. The answer is yes. Since ray tracing in Vulkan, they added device pointer. And you can basically get a 64-bit integer. Oh, where is it? Device address. Buffer device address. So you can get a proper address from a buffer. And all of that. Wait a minute. Support for buffer device address is mandatory in 1.3. I did not see that. Huh. I could just actually support this then, because wait a minute. Yeah, we might just go full on pointers then, because if you look at it, support for this is mandatory in 1.3, regardless of the extension support, because in my compiler, right, we've got a restriction on Vulkan 1.3 anyway. And if we have a restriction on 1.3, we might as well just do the pointers then. Yeah, it'll take a bit of work though. Because I've sort of hacked pointers in at the moment. It'd be a very limiting thing. Yeah, I'll have to get inlining working. Because in Vulkan they have another problem. Yes, the compiler. Yeah, so that's for like the logical pointers. That's the idea. They need to see the target. Yeah, that type of thing. Yeah, that's the way of explaining it. But this means you get like proper like physical address pointers, right? So in SPIR-V, it enables this sort of like physical storage buffer thing and some other, like this storage class, right? So you can do like change the addressing model from logical to this sort of like physical 64 thing, right? So your shaders use that, and then basically, what else? What's the other thing? Yeah, so there's one more problem. This thing is one of the biggest problems with pointers. You can't and this is why WGSL, whatever it's called, the shading language, looks like a piece of crap, is because of SPIR-V storage classes. They do all this silly stuff with a like pointer, PTR, this, right? And they, you write the word function in there. Why is that? Because you have to know what sort of like storage class your pointer is, and it's really, really annoying. So it can come from a function, right? That means it's like on the stack, right? Or whatever. You've got private, which means it's sort of global scope. It's local to the invocation, to that thread. Wait, is that right? Something like that. Work group memory, so that's LDS memory, right? In AMD's terminology. And then there's another one, storage buffer for storage buffers, right? I think you got to use the special one for the physical addresses, yeah, physical storage buffer. So basically, how do you avoid this problem? So they want to make it explicit. That's not really a good way to do it. The easiest way to do it, the best way to do it is like shaders automatically fully inlined. Not much hardware supports like calling a function, so all shaders are typically inlined anyway. I think since like ray tracing, they've been able to do some form of like calling of a function or whatever. But from the point of view of SPIR-V, you still get functions, but they're all just get inlined anyway. Because there is no support for recursion, right? So the way if I were to add pointer support to the compiler, the way I'll do it is I'll basically just inline everything. When I inline everything, I have the full understanding of where the pointers are coming from, and I can then figure out like what storage class they need, and if there's any storage class incompatibility. Say if I say this is equal to this local variable is well, actually won't be that, will it? Because it's compiled down to SSA or something like that. Yeah, so it means I can basically work out where the pointers come from and then assign the storage classes from that, because I have the full understanding of the code. Yeah. I know, I think I might have to put an error if you put like a conditional statement and say, hey, it's equal to this local. Yeah, so you won't be able to do something like this still. If something, I don't know, something. Where you reach it from some buffer, right? You wouldn't be able to do that because the storage classes would be different. And that's still okay because it's better than nothing, and you still get proper pointers that way. But still, though, it's still a pain in the butt. So yeah, shader programming. Yeah. But it would help like reduce all this crap, right? I could just have a pointer, and this would just be very short and nice. you know. Yeah, fun. One day GPUs will be more programmable. But until then, so we'll deal with them. Ugh. Right. So anyway, where was we at before this? Oh. Yeah, so that's all good. So now we just make another shader and jobs are good enough, I think. So we just want to do the traversing code, going up the tree, do the visit bit thing. So I think we can just do a copy of this shader. This is how it always works, right? Just copy the current shader and do it slightly differently. So we're still on this traversal code going up the tree, but I think we just want to do a simple check. Or we just say if node, so let's go, if there is any, if there's any children, or if there's any spheres, then copy the node to the proper place. And then we want to be able to do some patching also. So this no longer refine. This will be known as a see, I think you just want to process 32 clusters at a time. At this point. Yes, it's not refine, it's more like so essentially you want to like you want to do like a final copy of the nodes into their persistent space, right? So copy to persistent or so essentially you're taking the nodes that you want to keep. Copy to destination or to persistent. Something like that. Or tree make persistent. Much better. Persistent. There we go. Make persistent. Beautiful. So you get the volume. Shoot, I've just realized. There might be a problem with this solution. So the problem is you can't do a full 1024 by 1024 grid of these guys in one go, because if not, that's a gigabyte times size of all whatever amount of memory that I need just to build this volume. Because unfortunately, you need to know the highest level of detail before you can simplify it. That's just the way the solution is. Well, that's just the restriction on the way it works. So because of that, we just do partial areas at one time. and just have a smaller amount of build space available in memory. So because it's in 3 dimensions by halving it, or maybe doing a quarter resolution, you've reduced it, you know, exponentially, you know, just crazy amounts, right? So you've dramatically decreased it. So because of that, we kind of need to make the nodes so the persistent copy. Okay, so you do this refine. For this, you would know, hey, which ones need to be removed? You're not actually going to remove them yet. Right. So maybe just do the shuffling. Yeah, maybe we need to shuffle it in build space. And then maybe there's a final, we need another shader then. One that shuffles it around in build space somehow, in the build allocation, just does the removing. And then another one which does it when it makes it persistent. 4 bits per cell. So half a gig. Unfortunately not, Rosmusco, because it would be even worse. We need a lot of information. We've got like say if you completely if I were to fill that 1024 cubed volume, you've got already let's be generous here and say we fit it to 2 bytes. So you've already got 2 bytes if it's to fill a whole volume. So that's already 2 gigs, right? It could have been 4 gigs if I didn't remove that, but yeah. Then this one is the clusters, where each one of those nodes at the highest LOD would be so you divide it by, well, yeah, it's the 2 by 2 by 2. Okay, so just be divided by 2, yes, so it should be 512. Yeah, so it'd be 1 gig times by size of this divided by 2. So it's quite a lot. Yeah, it's definitely a lot of memory just to build these things. If I were to do full 1024 out in one go. So because I can't do that, we're doing a smaller volume, maybe 256 cubed. And that will reduce it down to just like a few hundred megabytes all in all. So that'd be much better. Yeah. So it'll work with 256. Oh, that's in hex. So that's 16 meg. So it'd be 16 megabytes times by whatever, 2 bytes. So that's 32 meg for all the spheres. I think maybe we might have to times that by a half if we're doing a full LOD chain up to the highest or the lowest LOD or something like that. And then there's probably something to do with the cluster nodes as well. But it's definitely a feasible amount of space. It's not gigabytes. It's a couple of hundred, maybe it's like 250 megs at most for build space. So it should be ideal. And the bit set fits in there nice and easy as well. So it just means I have to run these shaders, free up some space, run the shaders again. So when you do this refine node, the whole point of running the refine is so you can identify and free up the space. So when we delete these nodes, then what could we do, right? Like I can't delete them in place. You'll get holes. Um, um, So if you pass through a node, you could be like, hey, I'm at the end of the array. No, because multiple of those could happen at the same time on different CUs, and you'll miss it. So you can't do that solution. We could keep the same solution that we're doing, perhaps. You then traverse up. You could copy it to another space, right? And you're only copying the cluster nodes. You could definitely free up. We didn't free up the spheres here, so you could free up the spheres. Yeah, so we need to. So maybe we, so maybe you can free those, right? So you free the spheres up, but then. So that's what's going to take most of the space, but ideally you need to free up this node as well. So in the second pass, how could we arrange this other pass to essentially shuffle the nodes around? So you want to do like basically a shuffle delete. You don't have all the nodes in a linear array. You could do, but if you did, we can maybe have a bit. We could maybe store a bit on each node. Or maybe just have a bit set for each node. Sorry. A bit set for all of the nodes that you want to keep and delete. And you can just run, you just run a shader over it. So if you had a bit set for where each bit represented a node, and you just say you want to keep it or not, you can dispatch where each thread gets a node, maybe. Each thread gets a node. If the thread's going to be deleted, you scan over from the left-hand side, and you see if you can find a bit that is set. If the bit is set, you try and claim it as your own. If you can claim that bit, you then do the copy into your place, and you've removed the bit, right? If you can't remove any bits on the left-hand side or the right-hand side, whatever way you're doing it, then it must mean that you are the furthest left, and you leave that alone. Yeah, I think that's the way you can do it. So we want to have a way of like shuffling and deleting. Yes, you need to have a way of like call it shuffle delete. So I think the idea could be something like you just get a node. So it's just known as a node index. The problem is it's kind of like an S. Oh yeah, it's from the leaves, isn't it? Yeah, so you want to go like take away leaves. So you could definitely overflow this. So I guess you just say, if node index is greater than volume. There's a non-leaf nodes count as well. And then you want to reduce that number by the leaf nodes count. Make sure that's signed. Cool. What do we pick? Simpler to pick a smaller maximum size per volume and use more volumes instead. So what's nice? Yeah. So yes, what you're saying is just have the limitation be 256, 256. Like having a big space to, yeah. So the biggest problem is also so the nice thing about having 1024 cubes is that you've got 10 bits. And you got 10 bits, which means it fits into Morton 10-bit very well. So when we do the BVH, it'd be nice. There's that benefit for it. There's also it gives us a range. We can say, we can say in the editor, like, hey, this thing I'm constructing, the smallest unit is 1.6 mil. And that would then mean that the maximum is like 1.6 meters of space or something like yeah, it gives us like this nice big range basically. And if we were to take away, we're taking away 2 bits at that point. And it will give us, what would it give us? So 160 mil. It gives us 40,000 mil. Which is what? Which is 40 meters. Maybe that's not bad. Let's try at the lower. Okay. 1.6 mil times 256. I'm not sure if I want to go that small, but it's just the idea, right? Maybe that's the smallest unit. But yeah, so it'd be like yes, that wouldn't even reach a meter, would it? It reaches 0.4 meters. It reaches like 400 mil. So yeah, you basically are dealing with so that the maximum size like volume you could build at that point with a unit that's as small as the smallest sphere, 1.6 mil, which is proper small, would be the maximum volume size would be about 400 mil. So that is, so that'd be a meter. Yeah, so it's nearly like half a meter. So that's if you use the smallest unit spheres. Being proper diddy. And considering the art style, I'm not sure what sort of size we want to do. What sort of size, minimum size we want to have. But yeah, maybe it's something we can do. It just gives us less range. Rather than having 10 LODs, we'll have 8 LODs. But maybe it's fine. Most body parts fit within that. Yeah. It's a bit of a restriction though. But yeah, ideally you do want to have each body part, right? But 1.6 mil is proper diddy, right? It's tiny. And I probably don't want to go that small, but it's kind of interesting if you could go that small. Because then things are like proper. You know, I'm not sure if we want to have like bigger spheres and that sort of style, or they're so small that it's yeah, it's questionable. I'm not sure if I'll be able to render that many to be honest, but we're gonna try. But say if we just doubled it, right? Say if the smallest unit was 3 mil, right? That's maybe enough, right? That's nearly a meter, and then that's most body parts, right? The only problem is won't be able to do a whole meter, which is, you know, a meter is a good measurement to aim for. So maybe just do 1 meter divided by 256, and that's the minimum, right? So the minimum is maybe 4 mil. So we did 4 mil at minimum. All right, that should be back. How much simpler would it be? That is a good question. First of all, let's get the tunes back. These have probably been off for a while, but huh? Right. That ought to be good enough. How much simpler would it become? That's a good question. Because if we did a restriction of 4 mil, which is still quite small, right? 4 millimeters. I haven't got a ruler here, but that, you know, ought to be good enough. For my finger, it could probably, you know, you could probably put a, you know, like 3 or 4 spheres across it, and that might be enough. And then you do like, you know, you could do like fingers with it. Yeah, I haven't got a ruler around. Yeah, a mil is probably small. Like a centimeter, that's a centimeter. Yeah, 4 mil is proper diddy. So maybe 4 mil should be enough, and then that'll fit. And then it's not really a meter, right? It's 1024. So this, how much simpler would it become? Then we won't have to do multiple passes to build a volume. We can simply say we can simply first of all, this shuffle delete wouldn't have to exist, right? You wouldn't have to do that shuffle delete code. We could just copy it directly into the persistent space. We can just do that make persistent thing and do the delete while we're copying it into more of a persistent space, right? Yeah. So this means we could, when we dispatch our shaders, we can essentially just, you know, dispatch all shaders to sort of build a volume, right? And it will probably have like just like 5 shaders or whatever, and then we can put some sync between it and then do another one. And maybe there's like, maybe we can time this, and we'll know, you know, for a, we can see how complex the volume is, and we can estimate how long it's going to take, and we can basically budget this. And it would be better to budget that way as well. It'll be quicker, right? Yeah, I think we should go that route. That sounds like a good idea to me. If we did that, then we can actually use less bits. We can use 8 bits instead of 10 bits for things. And it's fine. It doesn't fit perfectly into more than 10 bit. If it fits into more than 10 bits, that's good enough. Yeah, so maybe, I think we'll do that. Sounds like a good idea. So if you have these guys, you do the copy, right? Copy node to persistent space and patch the parent node in non-persistent space. I spelled that wrong. Oh, it's persistent, damn it. English. Damn it, English. And then this one, you'd need to delete the sphere memory, right? Delete the sphere memory. We could have done it earlier, but here it would probably be better. You could use 1 or 2 DIMMs with 10 bits if you want a middle ground. That's good. Yeah, that's another good thought. I think yeah, the thing is though, is 256 squared is a nice amount of memory. You know, it's not, it was 16 megabytes multiplied the number of bytes per element or whatever, you know, it's not that bad for build space. And as soon as we start adding more across the dimension, it starts multiplying it by 2 each time, doesn't it? So, yeah, it's a good idea though. I think let's avoid that though. Yeah, that comment to delete the memory, wouldn't it? I'm not going to do that anymore. Yeah, so that would be ideal. So we just need to sort of make persistent BC thing. Oh, this is going to be amazing. So how many shaders we got left to do? That's the question. This has been very complicated. We've made... How many shaders we've made? Figure this one out. 1 shader, 2 shader, 3 shader, 4 shader, 5 shaders. So there's 5 shaders we have to do. So in that profiling thing, we'll probably have to make like a little way where we can group these into one sort of, you know, we can basically group shaders together and profile them as a unit as well. Because it's going to be a lot of noise when we start doing multiple of these. So this one you'd basically need like a, you know, hey, here's the new volume. Here's the new volume. Sphere's midpoint or whatever. Yeah, we need to count. We need to count them up. No. It has to get allocated somewhere. Yeah, someone we've got to figure out. Yeah, so we've got to write this shader. What other shaders do we have to write? We have to write another shader which sort of downsamples. There's a custom downsample. There's gen occupation map downsample, and this shader has to this makes it on the highest level of detail. Maybe you do it all in one pass. No, it gets a cluster per. It does a cluster. Yeah, a cluster node per thread. So you don't need LOD here, but you need it here. No, you would do like a destination source. We don't need the cluster nodes. Read only from that one. And you shouldn't have to read the volume either. So it'll be a custom downsampler because there's repeated bits from the neighboring bit sets. And they need to sort of downsample in a very special way. So we need, rather than gen, downsample. Excellent. So we've got to build that shader. That'll be quite simple. We've got to finish off this shader here. This new one here, this make persistent. You're gonna have to allocate the node memory as well. And then I guess we can start wiring this thing up. That's also going to take some time as well. But we're on the way out of things. This is so complicated, but it's coming together. Oh my days. So we've got to change the plan a bit. The plan is probably going to do a 256 by 256, and we'll probably have a minimum of 4 mil. Or we did a minimum of 4 mil. Is it 250 that you need, isn't it? Yeah, 250 times 4. And that'll get you 1 meter. So you could do each body part in a meter easily, right? No, meter's not that big, right? Yeah, meter's a nice unit to say the maximum. If you use the smallest, the absolute smallest size for a sphere, and as you increase that, the maximum grows bigger as well. So you did 8 mil, you get 2 meters max. That sounds ideal. Awesome. Right. So yeah, there's so many comments that need to be cleaned up as well, where it's just all wrong. Because I've just been trying to think about how I want to structure this thing. Getting good. Right. So hopefully next stream we can sort of get the skeleton in for these shaders, these 2 new shaders, and then the streams after that we can sort of try to get this thing. Try and think about the code that sort of fires these things off, right? And get it compiling or whatever. Right. So our next be on Thursday at 7:30 p.m. GMT. And also stream on Sundays as well. That'd be at like 6 p.m. GMT. There's like a Discord channel if you're gonna come and hang around. And that's about it for now. Let's find someone to raid. Is anyone on here? I need to figure out how to. Right, classic Twitch. There we go. Um, There we go. Found some CPPs, right. Thanks, kind of everybody. Good to see you all. Hope you have a good start to your new year. Yeah, I'll see you all in a future stream. And hopefully we're on the outward curve of this this complicated system. Oh my days. It's going to be awesome. Right. Catch you later, guys. Have a good night. Thank you. Bye-bye.